This is MA266 Exam 1 from Fall 2024. We'll go ahead and get started with question 1, which is asking us to identify a slope field that corresponds to this given differential equation. So first, remember what a slope field is. It's a graph showing the slope at every point corresponding to this equation, right? So y prime is our slope. Our slope at any point xy is equal to negative x times y. I like to do these by just kind of going through and checking points. These are usually pretty straightforward questions. Easiest thing to check first is the origin. So y prime at 0, 0 is going to be negative 0 times 0 is just 0. So all of our origin slopes should be 0. In slope field A, we do not have that. We have almost a vertical line, so it cannot be slope field A. In B, we do have a slope of 0 at the origin, right in there. Same thing with C and D and graph E down here. So now let's move on and see what else we can check. Because our y prime is equal to negative xy, that means any point on either the x or y axis should also have a slope of 0, right? Any x value with a y value of 0 or any y value with an x value of 0 is going to equal 0. 0 times anything is 0. So our whole vertical and horizontal axes should have slopes of 0. We've already ruled out A, but we could see we would be ruling it out again because we do not have slopes of 0 along the x-axis. In B, we do have those slopes of 0 along the x-axis, but we do not along the y-axis there. Those look like slopes of negative 1 or so. So we can rule out slope field B. And then C looks good. We've got 0 slopes there and 0 slopes there. If you kind of interpolate between the two, we're given. Same thing with D. E, we're good along the x-axis, but we do not have slopes of 0 on the y-axis. We've got, it looks like, slopes of infinity or vertical lines. So we can rule out E. This leaves us with just C or D. I'll rewrite, remember, y prime is equal to negative xy. And we can see the main differences between C and D. They seem to be kind of inverses of each other, right? So in the first quadrant of C, we've got a positive slope. First quadrant of D, we have a negative slope. So let's just plug in a point and check. Let's plug in 1, 1 in the first quadrant. That would give us y prime is equal to negative 1 times 1. Y prime is equal to negative 1. So we should have a negative slope at 1, 1, or at any point in the first quadrant here. See that in C, we've got a positive slope in the first quadrant, so that can't be right. And we can confirm that in D, we've got a negative slope in the first quadrant, or at 0.11, so that means D must be our correct answer here. You could go through and check other points if you want in D and make sure that everything comes out to y prime equals negative xy if you want to be sure. In problem 2, we are told to use separation of variables to solve this initial value problem. So here is our given differential equation, and then our initial condition that makes it an initial value problem. Remember that for separation of variables, we need to get to a form where all of our x terms are on one side and all of our y terms are on the other, so that we can then integrate both sides. So we need some function in terms of x, dx, is equal to some other function in terms of y, dy. Right away, you can see we're going to have a little bit of trouble because we've got x terms and y terms mixed in both the numerator and denominator of our fraction. What you'll notice, though, if you look at both the numerator and the denominator, is that you can factor. Whenever you have terms mixed like this, there's going to be some way, some trick, or something you can use to separate them out. So I'm seeing that we can factor a y squared out of the top and an x squared out of the bottom. So we'll leave our left side alone for now, and then factor the top. That will get us y squared times 4x squared plus 1 over x squared times y squared plus 1. And now our terms are isolated by variables. So this is only y's, that's only x's, only x's, only y's. That means we can multiply all of our y terms to one side and keep all of our x's on another. So I'll multiply by y squared plus 1 and also divide by y squared on both sides. So that will get us y squared plus 1 over y squared. And then we'll keep dy dx. And then that leaves us with just our x terms over here, 4x squared plus 1 over x squared. Now the only term left on the left side that's not only in terms of y is that dx, and we can just multiply that across. So we'll get y squared plus 1 over y squared dy is equal to 4x squared plus 1 over x squared dx. And now we're set up to just go ahead and integrate both sides. Throw an integral there, and we already have our differentials from the dy and the dx, so we can do this. The easiest way to do this is just separate out your fraction terms. So on the left side, we've got the integral of y squared over y squared is 1 dy plus the integral of 1 over y squared. I'll write that as y to the negative 2 dy. And that's equal to the integral of 4x squared over x squared is just 4 dx. And then plus 1 over x squared, again, I'll write that as x to the negative 2 dx. You could keep these as single big integrals if you want, it doesn't matter. Alright, so integrating across from the left, integral of 1 dy is just y. And then we have integral of y to the negative 2. That's going to leave us with a y to the negative 1. So that's going to become negative y to the negative 1. So minus 1 over y. I'm going kind of quick through these integrals just because you can work them out on your own if you need to. I want to focus on the diff-eq part. And then on the right side, we get 4x. And then again, we'll get minus 1 over x. And then don't forget your plus c. These are indefinite integrals. We don't need to add a plus c after every integral because they're just arbitrary constants. We can combine them into one big plus c. So we'll throw a plus c over on that side. And then I actually think it's going to be easiest to solve for c right now before we do any more simplification. So we know that y of negative 1 is equal to 1 from over there. So when x is negative 1, y is equal to 1. Let's just go ahead and plug that in. I'm going to leave this, that's our general solution. And then we can work in blue. If we start plugging in 1 for y, we get 1 minus 1 over 1 is 1, equals 4 times we're plugging in negative 1 for x, so it equals negative 4 minus 1 over negative 1 is just plus 1 plus c. So that means 0 is equal to negative 3 plus c, so c must be equal to 3. That then means we can plug our c back into our general solution. So y minus 1 over y equals 4x minus 1 over x, and then plus 3. And then we can just rewrite this in the form that they have all of their answer choices. So isolate that constant. That gets y minus 1 over y minus 4x plus 1 over x is equal to 3. And checking this against answer choices, it looks like that's going to match answer choice B. So answer choice B is correct for this separation of variables IVP. In problem number 3, we are given a differential equation and asked to find the general solution. So the first thing that you have to do is figure out what type of equation this is and what type of method can be used to solve it. You probably recognize that this is pretty close to the form of a linear differential equation. So we have that dy dx or y prime term there, a y term right there, and then a term on the right-hand side with no y and only our independent variable x. Remember, a linear differential equation is in the form y prime or dy dx plus some function in terms of x times y, and that's equal to some other function only in terms of x. So in order to make this differential equation look like that, all you have to do is divide by e to the x everywhere. So I'm going to rewrite dy dx as y prime just to keep it a little bit cleaner. So y prime plus, I'm going to write this as times e to the negative x. It's all the same. This will just keep things cleaner. And then before we multiply on this right-hand side, I'm going to simplify this a little bit, or rewrite it, I guess. So 2ex plus 2e to the negative x can also be written as 2e to the x times e to the 2e to the negative x. Again, this is just like e to the x times e to the y is equal to e to the x plus y. I just went backwards. It'll make sense. Oops. It'll make sense why I did that in a second. So we will write this as 2e to the x times e to the 2e to the negative x, and then multiply it by the e to the negative x. Now you can pretty clearly see that cancels with that. So our final linear differential equation is y prime plus 2e to the negative x y equals 2e to the 2e to the negative x. When I actually took this exam, I had a lot of trouble with this problem because I mixed up some of my exponentials, so just be careful with what level everything is on. This is now our linear differential equation, which means to solve this you can use an integrating factor. Remember, integrating factor is rho, which is equal to e to the integral of whatever the term in front of y is, so that 2e to the negative x. When you integrate, there should be a dx there actually. When you integrate that, you'll get e to the, that'll be negative 2e to the negative x. And now what you need to do is multiply your entire differential equation by that integrating factor. So distribute it to every term. Jump down here, that will get us e to the negative 2e to the negative x times y prime plus 2e to the negative x e to the negative 2e to the negative x times y is equal to 2e to the 2e to the negative x times our integrating factor e to the negative 2e to the negative x. Alright, and then what you should notice is that these will cancel. Right, not that integrating factor there, just right there. And that will leave us with just a 2 on that right-hand side. So e to the negative 2, e to the negative x. I'm not going to re-say this all, I'm just going to copy it down. Great. Now, on the left-hand side, you need to recognize the product rule. Just like with every linear differential equation, it's not quite as easy to see here because you cannot easily take the derivative of this in terms of x. However, what we really have here is e to the negative 2, e to the negative x times y, the derivative of all of that, right? This is just product rule. This term is the derivative of that, and then this term is the derivative of the first half times the second. And then on the right-hand side is still just a 2. Now to solve for y, because we have that prime on the left-hand side, we can integrate both sides with respect to x. Integrating the derivative just gets us the original function, so e to the negative 2, e to the negative x times y. And that will be the integral of 2 is just 2x. And we'll throw our plus c over on that right-hand side. There would be a plus c on the left-hand side, but because they're both just arbitrary constants, we can subtract it over and combine them into one different plus c. Awesome. And now all we need to do is solve for y. So dividing both sides by e to the negative 2, e to the negative x, that will get y is equal to, looks like they did not factor, so we'll write individual terms. 2x e to the 2e to the negative x. Again, I just got rid of that negative in the exponent and I'm not writing it in the denominator. Plus c e The one important thing to note here is that you got to put your c in right after you integrate. You can't wait until the end, otherwise you'd be missing this term from your c. And go ahead and compare this to answer choices now, and it looks like this will match answer choice E. In question 4, we're being asked to find a general solution to the homogeneous differential equation using the substitution v equals y over x. So we're given a differential equation here. This doesn't match any other form that we know. And our substitution is v equals y over x. You can rewrite that as y equals vx. And then because we're going to be plugging in, we can see that there's a y prime term. We will also need the form of that in y prime. So take the derivative of this. Remember product rule here. We get v prime x, because derivative of the first times the second, plus derivative of the second times the first is just plus v, because the derivative of x is 1. So these are the substitutions we'll be using. We can go straight to plugging that in now to the differential equation. So x squared times y prime we just found is v prime x plus v. And that is equal to x times y, which is vx. Again, just pulling from substitutions right there. Plus x squared. E to the y over x is v. So let's distribute both sides. We'll get x cubed v prime plus x squared v is equal to x squared v plus x squared e to the v. You'll see those two terms are the same, they cancel out from both sides, and we can get rid of an x squared on both sides from those two terms and just be left with x and e to the v. So x v prime is equal to e to the v. To see what's next, I like to rewrite v prime as dv dx. And then you can probably see now this is a pretty simple differential equation. You can solve it just using separation of variables. So we need to move all of our v terms to that side, all of our x terms to that side. That will leave us with 1 over x dx equals 1 over e to the v dv. Again, I just divided an x from the left-hand side, multiplied by dx on both sides, and divided by an e to the v on both sides. So this is now another differential equation. We can just solve this by integrating both sides. The integral of, here I'm going to move this over to the left-hand side. The integral of 1 over x dx is just ln x. Don't need to worry about the absolute value because we are told to assume x is greater than 0. And that is going to be equal to, you could rewrite integral of 1 over e to the v as integral of e to the negative v dv. And then it's a little bit easier to see that that is negative e to the negative v. And we also need a plus c in there because these are both indefinite integrals. Remember, there would be a plus c coming from that integral as well, but because they're just both arbitrary constants, we can subtract from the left-hand side and just combine them into that 1 plus c on the right-hand side. Right, so there would be a plus c right there, but then we subtract. It would be a different plus c than we currently have. All right, our goal ultimately, remember, is still to solve for y. In order to do that, first though, we have to solve for v. The v in this equation is right there. So we are going to work on isolating that. Let's start by isolating that negative e to the negative v term and just moving over our c. That'll leave us with ln x. I'm going to keep this as a plus c. The reason I can do that is because this c is arbitrary. So when it's over here, it would just be the negative c as it is over here. Really, I should label this like c0. I'll probably drop that though and just keep writing c. And then that leaves us on the left-hand side with negative e to the negative v. Can get rid of that negative ln x minus c0, but again, I can just leave this as a positive for the same reason that constant is arbitrary. It can be whatever we want it to be, and we haven't defined it yet. And then e to the negative v. Now, to isolate something in a case like this, we have to take the natural log of both sides. So that will leave us with, moving up here, natural log of x plus c, oops, there's a negative there, plus c, and then natural log of the right hand side is ln e to the negative v, but natural log and e are inverses, so that side is just negative v. We can move the negative over to the left hand side and get negative ln x plus c is equal to v. And then remember that v is equal to y over x. So this means that negative ln x plus c is equal to y over x. And we can finally solve for y by multiplying everything by x and get y is equal to negative x ln x plus c. And that should match one of our answer choices. Yeah, that'll be answer choice A. They just reverse the order of the c and the natural log x. The hard part about this problem is really just keeping track of your signs and your natural logs. Other than that, it's not too tricky of a problem as long as you can get those substitutions in, and be sure to remember your power rule when you're finding y prime there. In question 5, we are asked to consider a population of fish regularly harvested and has population x of t, modeled by this logistic with harvest differential equation. Right here we're given for x prime, and then we're asked which of the following is true about the critical points of the system. The fact that it's logistic with harvest isn't really relevant here. If you remember the graphs and want to draw it out, you can do that. I think it's easiest to just solve as a regular critical point stability problem, though. In order to do that, we need to find all of our critical points. Remember, a critical point is when x prime is equal to 0. So we can set our differential equation here, this side equal to 0. 0 equals x times 6 minus x minus 8. Distributing that out, 0 equals negative x squared plus 6x minus 8. I will flip the sign to make that easier to factor. And then that factors nicely into x minus 4 times x minus 2. So that tells us that we have critical points at x equals 4 and 2. Right away, this can rule out some answer choices, but we'll keep going. To find stability of critical points, you always make a number line and then plot the points in order. So we have 2 and 4. And then the easiest way is just to test points and find the sign of the derivative at each section. So below 2, an obvious number to test is 0. We will plug 0 in for x here. That gives 0 minus 8, negative 8. So our x prime, our derivative there, is negative. Between 2 and 4, let's test 3. That'll be 3 times 6 minus 3 is 3, minus 8. That'll get us 1. So there, our derivative is positive. Finally, a number greater than 4. It's easy to test 6 because of that term there becomes 0. That leaves us with just x prime equals negative 8. So again, derivative is negative. Now draw in arrows. Negative points to the left, so coming away from that 2 on the left side, we have an arrow pointing to the left. On the right side, we have an arrow pointing to the right because that's positive. From the 4, we again have an arrow to the right because that section is positive. And then on the right-hand side, we have a negative there, so that arrow is pointing to the left into the 4. When you have arrows pointing away from a critical point like that, that is an unstable point. So x equals 2 is unstable. And then when you have arrows pointing into the 4, right, that's where the function wants to settle. That is a stable critical point. So x equals 4 is stable. And then checking answer choices, A assumes critical points of 0 and 6, which isn't right. What they want you to do is forget that 8 there, but it's there, so don't. Choice B says an unstable point at 2 and a stable point at 4, which is correct. Problem 6 is an Euler's method problem. We're told to use 3 steps of size 1/3 to approximate the value y of 1 of the solution to this given differential equation. We're also given our starting point at y of 0, which is equal to 0. Euler's method problems are really just about staying organized. They're usually pretty straightforward. I like to make a table to do that. First column of your table is your independent variable, which in our case is t. We know that we're starting at 0, because that's what we're given here. And we're going in step sizes of 1/3, so our next t will be 1/3, then 2/3, and then 1. Our second column will be our dependent variable, so y. And what we're ultimately looking for is y of 1, so we're looking for what goes in that box. We know that our starting point at t equals 0, y is also equal to 0. Our next column is going to be y prime, and then delta y, so your change in y. Start by finding y prime at this initial point. So again, we are given our equation for y prime, so 18 ty minus 1, y is equal to 0, t is equal to 0, so y prime is just negative 1. That means that delta y is our change in y over our change in t, so dy dt, y prime times our step size, so times 1/3. So this is negative 1/3. This means that our next y value is going to be 0 minus 1/3. Can now find our second y prime. So that's going to be 18 times 1/3 times negative 1/3 minus 1. And that is going to be 6 times negative 1/3 is negative 2, minus 1 is negative 3. So y prime is negative 3. Again, multiply that by step size to get the change in y, which will be that times 1/3, so negative 1. Now find our new y at t equals 2/3. It's going to be negative 1/3 minus 1, so that's negative 4/3. Can find our new y prime, and that will be 18 times 2/3 times negative 4/3 minus 1. And that's the same thing as doing 18 divided by 9, so 2 times negative 4. So that's negative 16 minus 1. I don't think I did arithmetic right there. This is 18 times negative 8 over 9, which is 2 times negative 8. So negative 16 minus 1. Okay, yeah, that's negative 17. So y prime is negative 17. That means our delta y is negative 17/3. And then to find our new y value, we can just add negative 4/3 and negative 17/3. That'll be negative 21/3, which is negative 7. So our answer is choice E. Y of 1 is approximately negative 7. In problem 7, we're asked to find a differential equation whose general solution is this. Usually these questions that are kind of asking you to work backwards are testing whether you understand characteristic equations and how to use them to solve homogeneous differential equations. You'll notice that this equation is in the form you'll get when you have 3 distinct real roots. So we see from this first term, our root is r equals 2. From the second term, our root is r equals 1, and then r equals negative 1. This is coming from the fact that every root in a characteristic equation for a homogeneous differential equation will result in a term like this, where you have c e to the root t, or whatever your independent variable is. So here we have three roots. There are no t's being as coefficients, so we know there's no duplication. These are real roots because there's no trig terms. So we can work backwards now. We know that the characteristic equation that must have resulted in the solution would have had these three roots. The easiest way to set this up is r minus 2 times r minus 1 times r plus 1 is equal to 0. This might not have been exactly what our equation looked like. It could have been in any sort of different form, but as long as it's equivalent, that's fine, and this gets us the three roots that would result in this. We can now multiply this out to get what our original form of our equation might have been. We'll start with the first two terms and get r squared. Actually, we'll start with the second two because we have the difference of squares. So we'll have r minus 2 times, and that'll become r squared minus 1. And then multiplying this, you'll get r cubed minus 2r squared minus r plus 2. And then remember, when we plugged in our characteristic equation, if we were solving this normally, you can think of it as r to the 0 corresponds to just y, right? So that's going to be a term like this, where you don't see the r. An r corresponds to a y prime. An r squared corresponds to a y double prime. And an r cubed corresponds to a y triple prime. This is the part that's easy to mess up. Don't start at r corresponding to y prime. So now we know that some sort of differential equation must have resulted in this characteristic equation using these substitutions. So we can just kind of continue working backwards. That r cubed, there must have been a y triple prime. Minus 2, to get that r squared, there must have been a y double prime. And then to get that r, there's a y prime. And to get that 2, or just the blank 2 coefficient, there must have been just a y. And we can keep that equal to 0. So you can see this will match up with answer choice C. If you're still confused on how we worked backwards, we can kind of redo this going forwards, and then that'll help make sense. If this makes sense to you, though, that's the end of the problem. If we were given this differential equation to solve, we would use a characteristic equation because it's a homogeneous differential equation. So we'd plug in our substitutions up here. We'd have r cubed minus 2r squared minus r plus 2 is equal to 0. And then you would factor this. We know from here that this will factor nicely into r minus 2, r minus 1, r plus 1, which means roots are 2, 1, negative 1. And then if we were to write this in the form of our solution, we would get y of t is equal to, every root is going to have a corresponding term because there are no duplicates. So c1 e to the 2t plus c2 e to the t plus c3 e to the negative t. And this is where we started working backwards from. Hopefully that helps clear that up where we went. Question 8 is our first free response question. We are given an initial value problem. This differential equation here is a linear homogeneous differential equation. We know that because the right-hand side equals to 0, and then all of the linear terms in terms of y double prime, y prime, and just y on the left-hand side. Easiest way to solve linear homogeneous differential equations is with a characteristic equation. So remember, in a characteristic equation, for y, we're just going to plug in 1. For y prime, plug in r. Y double prime, plug in r squared. So the characteristic equation will become r squared plus r, or plus 6r plus 9 is equal to 0. This factors easily into r plus 3 squared. I'll just write it as r plus 3, r plus 3. So this means we have roots r equals -3 with a multiplicity of 2. This multiplicity changes how we write our general solution. So y of t, I don't think we're told what the independent variable is, so I'll use t. Y of t is equal to, we start normal, where we have c1 e to our root, so -3, e to the -3t. But then because of that multiplicity, our next term gets multiplied by our independent variable. So we have c2 t e to the -3t. The difference here is that t, right? That doesn't exist in the first term. This is now our general solution. If we were only asked for a general solution, we would be done with the problem, but we're given initial values and asked for the specific solution. Go ahead and plug these in. We can see that we'll need both our y equation, which we've got right here, and y prime. So let's solve for y prime. Just take the derivative of y, bring down the -3 chain rule, so -3 c1 e to the -3t. And then we'll have to do product rule on this second term because we have both the t and the e to the -3t. So derivative of the first times the second, that'll be 1 is the derivative of t, so just c2 e to the -3t. And then derivative of the second times the first gets us, we'll pull down the -3, and then that'll be c2 t e to the -3t. Remember that -3 from chain rule. We can now start plugging into these equations. So we know that y of 0 is equal to 1, which means that when t is 0, y is equal to 1. We'll plug that into our first equation. So 1 is equal to c1 e to the -3 times 0 is e to the 0, which is just 1. So we just have 1 is equal to c1, and then that'll be 0 plugged in for t right there, which makes that easy because that term is just 0. So we know that c1 is equal to 1. We can plug into the second equation now. Y prime of 0 is also equal to 1. So 1 is equal to, this will become -3 c1, and then the e term disappears because that's just a 1, plus c2. Again, we lose the e term because all of that just becomes 1, e to the 0. And then this last term will completely disappear because, again, we've got that t right there. So that just is multiplied by 0. We can solve this now. We know c1 is equal to 1. We can plug that into the second equation. 1 is equal to -3 plus c2. So c2 must be equal to 4. And then to get our particular solution, we just have to take these initial, or these c values and plug them into our general equation. So our particular solution is going to be y of t is equal to, c1 is 1, so e to the -3t. Again, I took that and plugged it in there. And then plus c2 is 4, so 4t e to the -3t. And that is our final answer for this free response question. Problem 9 is asking for the general solution of the Bernoulli equation given here, and they give us the substitution v equals y to the -2. If they didn't give that substitution, remember the general form is v equals y to the 1 minus k, where k is that exponent right there. So here we have 1 minus 3 is -2. This problem's a little bit long, but it's not too bad. So first we need to figure out how to get that substitution plugged in. The easiest way to do that is to first, let's rewrite our substitution, v equals y to the -2, and then let's take the derivative of that because we will need to be plugging in a v prime as well. Ultimately, our goal with this substitution is to reduce this to a linear differential equation, and then you know how to solve that. So derivative of this, remember that y is a function in terms of x. So we do our power rule here like normal. You get -2y to the -3, but then you also have a y prime there. That's the chain rule coming out because y is a function. Then let's go back to our equation. In order to solve this, you need to divide this y cubed out of that right side. So turn this into y to the negative 3, y prime, minus, that'll be y over y cubed, so that'll become y to the negative 2 is equal to 4. Same equation, just rewritten. Now you can hopefully see some of the similarities between this equation and its terms and the substitutions we've got there. We obviously have this y to the negative 2 term, which will line up nicely with the v, and then this looks pretty similar to that first term, so we can make that fit in there. Let's start with the y to the negative 2. So that is just v, so that's going to be a minus v. The right hand stays as a 4. And then this first term, the only difference here is that negative 2, so we can just throw a negative 1/2 in front of there, and that's v prime. You can check that if you multiply negative 1/2 by that, you get that term. So now we have a differential equation only in terms of v and v prime, and at this point you should recognize that this equation is a linear differential equation. If this is where you got stuck trying to solve it, I would suggest going back and continuing from here, because you can probably do the rest. Otherwise, we'll keep going. Now, we just solve this like any other linear differential equation. First, remember, we have to rewrite it so that our first coefficient is a 1. So we get v prime, we multiply everything by negative 2. So we get plus 2v is equal to negative 8. It's a linear differential equation, so we find our integrating factor using that 2 coefficient. Remember, rho, our integrating factor, is equal to e to the integral of 2, again, because that's the coefficient on our v term, dx. And that is going to be equal to e to the 2x. We can multiply everything by that from the original equation, so we have e to the 2x, I'll keep everything color-coded, v prime, plus, that'll be 2 e to the 2x v is equal to negative 8. And now, like usual in linear differential equations, this one's pretty easy to see the chain rule here. All this actually all is the derivative of e to the 2x times v. Right, this is just, these two terms here are the product rule coming out of that. So that's all that prime, and that is equal to, oh, I forgot to multiply the right-hand side. Remember to do that. There we go. So that right-hand side just stays negative 8e to the 2x. Now we need to work on getting v, right? Because our ultimate goal here is to get y, but right now y is in terms of v. So we can start integrating. We've got a derivative here, so integrate both sides with respect to our independent variable x. That is going to leave us with just e to the 2xv on that side, and that'll be equal to, with chain rule, we'll have negative 4 e to the 2x. And then these are indefinite integrals, so throw on a plus c here. Like in other problems here, we would have a plus c on this side as well. It would be a different c than this, but then we would just subtract that c over to this side and get a new constant, but c is arbitrary, so it does not matter. Now, to isolate v, we can just divide everything by e to the 2x. So v is equal to, that will cancel out with the e to the 2x over there, so v is equal to negative 4. And then plus, I'll write this as c e to the negative 2x, same thing as c over e to the 2x. It's important to make sure you put your c in right after you integrate here versus waiting, otherwise you'll forget to attach that term to it. And then we are trying to find this in terms of y, or a solution for y, not v. But remember that original substitution where v is equal to 1 over y squared. This means we can go plug in for v right here. So that will get us 1 over y squared is equal to negative 4 plus c e to the negative 2x. Take the reciprocal of both sides, that will get you y squared is equal to 1 over negative 4 plus ce to the negative 2x. And then we can take the square root of both sides because we know y is greater than 0. We're not going to have any square root issues there. So that will leave us with y is equal to square root of 1 is 1 over square root 4, or negative 4, plus ce to the negative 2x. And we were just asked to find a general solution. We weren't given any sort of initial value, so that is our final solution for problem 9. In problem 10, we have a physics kinematics problem here. We have a ball with mass 1 kilogram shot upward from ground level with an initial velocity v0. It is subject to Earth's gravitational acceleration 9.8 meters per second squared. And then there's an air resistance term here modeled by k, absolute value of velocity, and then they give us a k value of 2. So in part A, we're asked to compute the velocity v of t, which will be a function of the ball before it reaches its maximum height. A few things to note here. First, remember F equals ma. This can also be written as m times dv dt. We'll of course define up as positive. We can start setting up our force balance equation. The forces acting on the ball at any point, there will be two. There will be the gravitational force and there will be an air resistance force. So we have force as a function of time is equal to, we'll do gravitational force first, that's just negative mg. And then our air resistance force is going to be minus kv. We have a minus here so that it's acting in the opposite direction of v, and that allows us to drop that absolute value. Right? If the ball is traveling upward, so v is positive, that means this overall term is negative because of that negative sign. So it's acting opposite the direction of travel. This is exactly what you'd expect. We can plug in some values that we know here. M is 1, 9.8 for g, minus 2v. Now we can start trying to set up an equation for velocity. This is where we use this part of that equation. We know that we have f here. This is our function. And then we can set that equal to m dv dt. So we can write negative 9.8 minus 2v is equal to m dv dt. Remember here m is 1, so we can divide everything by 1. It doesn't change, and we'll get rid of that mass term. And now we have a differential equation for velocity set up. At this point, you can solve this differential equation because it is just a linear differential equation. If we rewrite this, we'll get v prime, that'll be plus 2v is equal to negative 9.8. Solve this like any linear differential equation with an integrating factor. Rho will be equal to e to the integral of 2 dt. Remember that 2 is coming from the coefficient on the v term right there. Multiply everything by the integrating factor. So that'll get e to, or I should write this integral evaluates to e to the 2t. So then we get e to the 2t v prime plus 2e to the 2t v is equal to negative 9.8 e to the 2t. Here it's pretty easy to see the product rule that comes out here. That whole left side is e to the 2t v all prime. Again, this is product rule. Derivative of the first times the second is right here. Derivative of the second times the first is right there. And then our right-hand side is still negative 9.8 e to the 2t. Now we need to start solving for v. We can integrate both sides with respect to t. The left-hand side, we're taking the integral of the derivative, so that just becomes e to the 2t v is equal to the integral of this right side. When you do chain rule, will become negative 4.9 e to the 2t. And then we need a plus c in there. These are both indefinite integrals. Like we usually do, we're combining the c from both sides into this one c, because it's just an arbitrary constant. We can divide by e to the 2t and solve for v here. That will get v is equal to negative 4.9. These terms cancel. They're the same. Plus, I'll write this as c e to the negative 2t instead of 1 over e to the 2t. Now we have our function for v. I'm going to write this as v of t, just to be clear that it's a function in terms of t. This would be the general equation for our velocity, but we are given an initial value. That initial value is kind of hidden in this paragraph where we're told initial velocity v of 0 equals v naught. We can start plugging in to solve for that. We know v naught is going to be equal to negative 4.9 plus c, and then this entire exponential term will become just a 1 because it's e to the 0. We can solve for c now. C is going to be equal to v naught plus 4.9. And then we can plug this back into our general form up there to get our particular solution. So we'll get v of t is equal to negative 4.9 plus that c we just solved for, so v naught plus 4.9 e to the negative 2t. And that is the solution to part A. Moving on to part B, I'm going to move all of this up to give us a little bit more room to work. And part B is it saying, suppose the ball reaches its maximum height at time ln 2 seconds, we're showing that its initial velocity must have been 14.7 meters per second. So we have our velocity equation that we can plug into. The important thing to notice here is that when the ball is at its maximum height, its velocity is 0. It has stopped moving upwards, it's not yet moving downward. So v is exactly 0. This means that we can plug into this equation we just found and find that 0 that we're plugging in for v is equal to negative 4.9 plus v naught plus 4.9. And then e to the negative 2t was ln 2 seconds. Notice here that e to the negative 2 ln 2 is equal to e to the ln 2 to the negative 2, which is just equal to 1/4. So we can plug that in and we can move the 4.9 over to the left-hand side. We get 4.9 is equal to v naught plus 4.9 times 1/4. We can multiply everything by 4. 4.9 times 4 is going to be 19.6, I believe. Set that equal to v naught plus 4.9. And when we subtract 4.9 from both sides, we should get that v naught is equal to our answer of 14.7. And that is indeed what we were asked to show. So this would be enough to show that v naught does indeed equal 14.7.